morning. Here we are once again at the physics video lecture. Physics 2A, video lecture 27. I have some requests to discuss some homework problems, and I'll even start with the most recent quiz number 5. And so we'll do quiz 5, some homework problems that people are interested in, and then we'll move along in chapter 8, see how far we get. Okay, so I have that written down here. What do we have? So quiz number 5. And then chapter 7, 39, and 44. Those are good problems. Chapter 7, 39, and 44. And chapter 8. These are all great problems. Chapter 8, 27. So let's do those. Starting with the quiz, it was the cat burglar problem. And I'm just going to do it symbolically, analytically. Namely, we have a horizontal string anchored here. We have one at an angle theta anchored here. Okay. And if you put the theta up there, you'll notice they're the same. It's horizontal. And then we have someone hanging from here, which we'll just say is a mass M. Of course, you have to remember mg. In fact, I may have just put the newtons there. So the force, of course, we have mg, and we have two tensions. T sub 1 and T sub 2, and the net force is equal to 0. We're not going anywhere. So let's go ahead and set that up. So the sum of forces in x direction, I'll give myself a little room. Sum of forces in x direction equals 0. So what do we have here? We have pointing to the left T sub 1, so that gets a minus sign. And pointing to the right, we would have the projection along the dotted line. That's T sub 2 times the cosine of theta. So minus T1 plus T2 cosine of theta is equal to 0. And then in the y direction, we would have in the down direction minus mg, or however many newtons we're given, just writing mg. And then we'd have in the up direction plus T2 sine of theta is equal to 0. So to get T sub 1, the horizontal, let's see what we have here. We have T sub 1 clearly is equal to T sub 2 times the cosine of theta. And what's T sub 2? We can get that from the second equation. So that is equal to mg divided by the sine of theta times the cosine of theta. So you could say it's the, you could either say mg cotangent of theta, or you could do them individually. But yeah, that's how that problem is done. Good. Cat burglar. And for the machine, right, that gives you guys the quiz, it generates randomly the angle and the weight in this case. It generated them randomly. So everybody who's taking the exam or taking the quiz gets a different pair of numbers. Good, but that's why you always want to solve things analytically first anyway. Good, so that is that quiz number 5, and now let's look at these chapter 7 problems. That goes back to gravity, and those are some good problems. So chapter 7, we've got 39 and 44. I'll do number 44 first. Chapter 7, number 44. That's about an orbiting satellite. So 744. What do we have here? We have 600 kilogram satellite, circular orbit about Earth, at a height above Earth equal to Earth's mean radius. Let's go ahead and just solve this generally for starters. So here's our Earth, and we can characterize it by its mass and its radius. And here's our satellite orbiting the Earth. We can characterize it by its mass, and it's a circular orbit, so we have the gravitational force Gm over r squared. That's the force is equal to the mass of our satellite times the acceleration, which is centripetal acceleration. So that's how we set that one up. And we can see now we have G, mass of Earth, mass of the satellite cancel. We have 1 power of R canceling. So that's the general expression for the speed, or speed squared. Now in this case, R is equal to 2 Earth radii, because we're a full Earth radius above the surface of Earth. And so then we can say that V squared is equal to Gm over 2 Earth radii, and take the square root if you want to get the speed. So what else were they asking us for? So that's the satellite's orbital speed, the period of its revolution, and the gravitational force acting on it. So that was A. Like I said, take square root of both sides. Now the period of its revolution, so for B, we're just going to write V is equal to 2 pi radius over t, and then we'll solve for the period, right? That's distance over time. So the period is 2 pi radius of orbit over the speed, and then when you're 2 pi 2 Earth radii, that's the radius of the orbit, times V from right here. You can simplify analytically, but I'm just going to leave it right here because it's conceptually we're pretty clear on that. 2 pi, that radius, V that we found from up here. And then the force on it, this is an interesting question. The gravitational force. The gravitational force on it is actually back here. Okay. This is Newton's law of gravity. So G mm over r squared, mass times acceleration. Okay, mass times, it's centripetal acceleration, so mass times acceleration. So if you evaluate this expression here with r being able to being equal to 2 Earth radii and v as given right here, then you'll have the force. Okay, mass times acceleration. Okay, good. So that is just a good circular orbit problem. Should I put that in words, what I just finished off with for part C? Write that down. So F is NA, that's what we're looking for, and this was Gm over 2 Earth radii squared. Okay. There are other ways to get these things more, in terms of lowercase g. I'll just put this as a note. these kinds of things. G, because that's an easy number for us, 9.8 meters per second squared. That actually is gravitational constant, mass of the Earth, divided by radius of Earth squared. So you can always substitute this combination in for G for a simple number. Save you a lot of calculation. Okay, good. So let's look at problem 39. Problem 39, projectile fired straight up from the Earth's surface. South pole, North pole. I'm going to draw the North pole, okay? For whatever it's worth. So this is a gravitational problem using energy. So the main thing is to set it up correctly. So we're firing something vertically with a certain speed, 1/3 the escape speed. So if it's less than the escape speed, it's going to go up and come back, fall back down. How far from the center of Earth, and so forth, so on. And part B, the altitude, that's just the trivial conversion. So let's look at this. We're firing, just to make it easier, here's the radius of Earth, here's the mass of Earth, and we're launching a rocket straight up. Okay. So energy at A is going to be equal to energy at B, which is where it tops out. Now the energy at A is kinetic plus potential. It's 1/2 mv squared minus gmm, and we're starting at the radius of Earth, right? That's the potential energy for Earth is equal to the energy at B. Well, if the energy at B is when it comes to a dead stop. So there's no kinetic energy up there. It's equal to minus gmm over r. We can just do it lowercase r sub b. And I'll just put here r sub b is equal to radius of Earth plus h, if you want to know the height above the surface of Earth. Okay. So this is one equation that's true, but what is the launch speed? We'll number these things. One, the launch speed is 1/3 of v escape. Okay. And the escape speed is equal to the root. I don't even have this thing memorized. 2gm over the radius of Earth. But that's true. Okay. Yeah, v escape. Okay. So if we have 1/3 v escape, well, I'm not going to rewrite that. Okay, so that is the escape speed. I just looked at it, it's true. So we have 1/3 of that to be plugged into here. Let's go ahead and call that V sub A. And I'll make this look a little nicer. V sub A is equal to 1/3 of V escape, and this is V escape. So now we just plug those in, and we will have a single unknown of r sub b. You'll notice we can make things a little simpler. These masses cancel right there. But yeah, it'll be a couple of steps of algebra. So we have 1/2 and then v escape squared. V escape, v sub a squared. V sub a is this, so we have 1/3 squared is 1/9, and then v escape squared is 2gm over RE. Okay. So we have that. And we can simplify it a bit. Minus GM over RE is equal to minus GM over R sub B, which is what we're looking for. We're looking for that one. So I'm pretty much going to leave this right here because you'll have some nice simplifications. You can get rid of the 2, the G, GM, and you would have 1 over 9 RE minus 1 over RE is equal to negative 1 over R sub B. So we're looking for R sub B. You got another line or two of algebra, but yeah, that's a 1. But that shouldn't scare you, right? This is, you invert this, get rid of the minus, get rid of the minus sign, invert it, and you're there. So you're within one step of the answer. So that's how that's done. Conservation of energy, really nice problem actually. And of course, once again, the V escape was the speed at which this launched object makes it out to infinity, and then R sub B would have been infinity, and we would have just had a 0 on the right side. Okay, good. So that is problem 39 of chapter 7. And now let's look at chapter 8, problem 27. That's the one they wanted? Yeah. Chapter 8, problem 27. So this is our current topic, statics, we're even beyond that now, so this is a review. It's a good problem here. Problem 27, let's have a look. Okay, yeah, so this is a painter standing on a scaffolding or something like that. Someone standing on a scaffolding. So here, I don't need to put any numbers in, I just have to set this problem up. So let's see what we have. Got the board. The board has a length L, it's uniform, and it has a mass lowercase m. So at the center of mass, we have a force mg. I'll do the forces in blue today. Okay, so we have a force, the weight of the board, mg. And the board is a total length, capital L. Okay. We have somebody standing on the board, a distance d, a distance d from the end here. So there is a distance d. And this person standing here has a mass, capital M. So we have a force, uppercase mg, right there. So what's holding the board up is a couple of ropes. They made it nice. We have 3 ropes here. So we have a tension force here. These are 3 and 2. T sub 3 and T sub 2. And then we have one coming up at an angle, T sub 1, and I'm just going to write theta. So this is a perfect statics problem. We're going to need all 3 equations to solve for these 3 unknown tensions. So once again, what's given the length of the plank, the distance d is given, the mass of the plank, and the mass of our person there, or 700 newtons. Okay, so we'll say the mass of that person there is given as well as weight, mg. Okay. So we're going to have three equations, namely the two from the equilibrium conditions, and there are three from the equilibrium conditions, two from the force and one from the torque. So we'll just set these up and then we'll point at them. So we have the net force in x direction is equal to 0, and that would say that negative T3 plus T1 cosine of theta equals 0, right? That's the projection under the horizontal direction. Then for the sum of forces in y direction, we are going to have T2 pointing up, T2 pointing up, minus mg pointing down, minus lowercase mg pointing down. It's two vectors pointing down. And then we have the vertical component of T1 plus T1 sine theta equals 0. It's a 0 here too. And then we have the torque equation. Now we can measure the torque anywhere we want, but the left side here is a good spot to measure it from. Then these two forces, T2 and T3, produce no torque. Okay. So for the torques, we have clockwise torque. It's a minus sign, so minus capital Mg times the length d. And then we have minus lowercase mg times the length capital L over 2. So there's two clockwise torques, and the counterclockwise torque finally is plus T1 sine theta times the entire length of the board, L is equal to 0. So this is a set of three equations in three unknowns. And you have to start plugging things in. What you'll notice is the third equation only has one unknown in it, T1. So this is the one to solve first. Okay, so go ahead and number these, 1, 2, and 3. The third equation has a single unknown in it, T sub 1. Everything else is just a bunch of numbers. And yeah, whether you plug numbers in at this point or later, go analytical as long as you can. Okay, so T1, you solve for T1, then you can obtain T3. Okay, because then T3, my sign is T1 cos theta. You already have T1 multiplied by cos theta. Then you have T3. Same thing for T2 then. So you now have T1 as well. You had it down here. So for T2, you bring everything to the other side and plug in, and then you get T2. Okay. So I'll just put it here. Here's a note. Solve for T1 in equation 3 first, etc. Okay, good. So those are some good problems. That's a good level of a homework problem for us as well. And you see how crucial it was to set it up. There's no way anyone can just look at this and guess the answer. It's just not going to happen. You got to go through with you have to approach it systematically, and that is to say we drew our sketch and then we identified our vectors, wrote our equations down. So for that reason, it's a really good problem. You have to go through with the system, and nobody can guess the answer, but if you work your way through. At this point, we've done all the physics, okay? And then it's just a question of not making a mistake to get the answer. Good. Let's see how much time we have left today. Okay, excellent. So from here, we're going to move back into dynamics, and I'll review a bit. We have to remind ourselves of the moment of inertia and the torque, and we're going to combine those things. I'll erase everything. I'll set this up. So we're going back to rotational dynamics. And this is going to link, this is going to be the rotational version of Newton's law. What we left off with last time was rolling objects, and there we had kinetic energy, translational motion, rotational motion. So, and the moment of inertia played a big role there, and we're going to extend that. So let's just go ahead and I didn't bring any demonstrations in, so I'll just remind you, if we take a wheel and twist it and turn it, we have to exert a torque on it, twisting force, and then we can get it spinning. Okay. So I'll just put this as a recall. Twisting force, which is just torque. I could write it the other way around. Torque, which is just a twisting force, brings something into a rotational state. Produces rotation. Rotational motion. Ah, there we go. So a twisting force, torque, produces a rotational motion. So here's what we're going to do. We have a top view of a disk. I don't actually need X and Y axes here. We're looking at a uniform disk. And we'll look at, we'll just say out at point R, there's a point there, and we're going to apply a force, I'll use red, to this point with the intention of spinning this thing up counterclockwise. Okay. So we have, start with Newton's law, F is equal to mass times acceleration. And we're talking about this little point mass here, the little mass, which is part of the disk. Mass is part of the disk. Force is mass times acceleration. Now I'll take this Newton's law and multiply both sides by r. And this is a tangential acceleration. I'm not talking about the centripetal acceleration. I'm talking about the acceleration in the direction of the red vector for that instant in time. Okay. So m a tangential times r, but we know that that is m times alpha r, because we're spinning the disk up, and that's the acceleration, the angular acceleration. Okay, a times r, so there's my substitution, times r is equal to m r squared, I'll put parentheses around that, times alpha. So what we have here is interesting. We have a torque, and what is that mr squared but part of a moment of inertia? So mr squared times alpha and now I'm going to do a shorthand version of a longer proof. We're just going to say the net torque on this entire sum of torques is equal to sum of mr squared. I'll put a little I there. Alpha, because now we really are looking at the moment of inertia. This we're just going to call the net torque on the object, because you'll have all kinds of internal forces canceling inside. So you'll really just end up with, if you're just grabbing at one point and applying a torque, you'll really just end up with that one as the net torque equals I alpha. So this is Newton's law for rotation. And since I have Newton's law for translational motion up there, you see it's a very logical progression, because we have force is mass times acceleration. We have torque, which is a twisting force, is moment of inertia, which is rotational inertia, times angular acceleration. Right? They follow one from the other. So this is Newton's law for rotational motion. Yeah, so that's actually a pretty satisfying state of affairs. And we could extend that chart, except I don't want to write down the whole table of things. We can extend the linear chart. Remember, we had linear equations on one side and rotational equations on the other. We now have obtained the force version of that. Okay, so that's a real nice state of affairs. So let's do an example of this. And there's a lot of interesting stuff going on now. So my example is if I have an unwinding spool. So here's a spool, and it has a bunch of string around it. I'll make the string in red. And then I have a mass. And by the way, so spool of radius r, mass m. And then I have a mass down here. And we need to call it a different mass, so we'll use lowercase m. Lowercase m. And gravity is pointing down. There's the axle, and this thing is just unwinding, kind of like a yo-yo would unwind. Not quite the same. Get a spool. So let's make sure we know spool unwinding. There's the axle, and that's the axis of rotation. So now we want to analyze this thing. And we have two things going on now. So for the bottom mass, I have a tension and a weight. And for this bottom mass, it's just an old exercise we've done before. I'm going to go ahead and make the positive direction be down. Okay, so I'll have mg minus t equal to m times a. So that's one equation. Go ahead and box it in. But what about Newton's law for this rotating spool? We realize that there is a, let's see, radius here. So there's a torque, right? And it's the tension that's producing a torque. So I have, I'm going to work underneath this equation right here. So I have, for the torque is T times R, tension times radius. That's a force times a length. That's my torque. That's what's torquing this thing. And that equals I times alpha. But we have alpha R is equal to A. I'm going to make some substitutions. T tension times R the moment of inertia of a disk, so we're going to say it's a disk, I sub disk is equal to 1/2 mr squared. I'm pretty sure I had that on the board the other day. The moment of inertia of a disk, 1/2 mr squared, should be in your book as well. So we'll substitute 1/2 mr squared for I, and alpha is going to be A divided by R. Divide both sides by R here. So A divided by R. And how much of this should I do? This cancels one of the R's, R squared over R. Then from both sides of the equation, we get both of them. Okay. So this equation, I'll go ahead and formulate as T is equal to MA divided by 2. That's all that's left in that equation. So these equations allow us to solve for two unknowns, right? This tension is the same as that tension. These masses are not the same, right? This mass is our hanging weight, and this capital M is from our spool. Good, so I think this is even a problem in the book, in which case, or there's a similar one, in which case we could use that as a yes. As a problem. Good. Yeah, let me check the time. I think I'm going to, I'm going to assign a homework problem now, or a couple homework problems of just this type. And then I'll do angular momentum next time. Let's see here. Okay. So yeah, this one's been set up very thoroughly with Newton's law of rotation. So we have this unwinding spool. We had to do two different things. This I can erase here. And what I'll do is I'll assign a couple of problems and then discuss them a bit. So this would be homework 27, chapter 8. So yeah, we have one major So I'm going to write chapter 8 problems 58. It's a yo-yo problem. '58 and '90. I'll say something about each one. So 58 is this problem right here. But they're asking us to do it in terms of energy. And when we can, we love to use energy. So let's, got a spool. Yeah. So I've set this up and solved it, so this one we can completely understand. And we could just answer the questions on problem 58 using this force diagram. But they're talking about energy. So there we say E sub A is equal to E sub B. And it's going to unwind a certain amount. So the thing is this, the potential, it starts at rest, okay? The potential energy, we can just say is zero, and the kinetic energy is zero if we want, okay? Kinetic at rest, nothing's moving and it's not unwinding. So we could, at A, before it starts to fall, we could have total energy be zero. Then we would have 1/2 I omega squared plus 1/2 mv squared. This is just like the rolling race that we did last time. The kinetic energy would have rotational and translational kinetic energy. The potential energy would have dropped, so I'll just write minus mgh. Okay, that's how far this weight dropped from the original position. That's why it gets the minus sign, it went lower. So we know that V is omega R, and H is however much string unwound came out. And they are asking us for the angular speed. Good, and they give you some numbers. Don't plug the numbers in until you make sure you really understand it. Plug that, yeah, since I don't have you guys in front of me here, if you plug numbers in too early, your chance for understanding a problem just goes away. So make sure you just leave everything symbolic. You've got your picture, you've got your A and B, and then plug the numbers in towards the end. Good, so that's how to do problem 58. Now problem 90 is a version of this same one. These are some great problems. Let me show you problem 90. Problem 90 is that we have a uniform cylinder, okay, that's wrapped in a string, and this time the string is just held up here. So now this cylinder is going to unwind. You can imagine, you wrap a string around the cylinder and let go, it's going to unwind. And we're supposed to find a certain analytical value for the acceleration. So this one's completely analytical. And you want to ask about the rotation and the translation of this object. So it's a nice generalization of this problem, okay? There's only one mass, but the torque, again, is the tension times the lever arm. But now it's rotating and translating at the same time. They say in part C of the problem that you can solve it using the energy method as well. Okay. So again, this thing is fixed. As this thing unwinds, at any point in time, it's rotating about the center of mass, so torque is the tension times that lever arm there. And again, you're going to have to set up two equations for this scenario. I'm going to leave it at that. This is a great problem. Let's see how we're doing time-wise. Okay, good. We're going to call it a day. There's one more really important topic we'll do next time about angular momentum, and that'll complete this chapter. So still a lot to do. See you guys next time.